So, hello friends, today we are going to discuss questions from statics. Okay. And just 1 second. Okay. So we are going to discuss 4 questions from statics, and in the first question it is given that consider a bridge structure as shown in the figure, consisting of 3 equilateral triangular frames connected at hinges. The structure contains 7 massless beams, and every joint acts an ideal hinge. A car of mass m is placed at the bridge central beam. Assume that all the beams are massless, all connections are hinged, no bending moments, the support exert no horizontal reaction forces. Determine the internal forces in each beam. State clearly whether each member is a tension or a compression. Okay, so this is a basic question, and we can just draw the basic diagram. Okay. So we are having these as 3 equilateral triangles, and so these are the side supports, and this constitutes the 3 triangles, equilateral triangles, and let us call this as A, B, C, D and E. And we are given that a car of mass m is at the central beam. Okay. So we have a car, and therefore it will be in the mg at the downward direction. And so here we can write 2 reaction forces at point A. Let us call this as RA, and we have other one that is our RE, and all this basically all the triangles are equilateral. Therefore we can say that it will be basically symmetrical forces. So we can write that by symmetry, 2 vertical support reactions which are our RA, and that will be equal to our RE, and the weight mg will be equally distributed among them. Or we can do it otherwise also. We can write it like as our force in the vertical direction. So we can say that our RA plus RE is equal to mg, and RA and RE are equal. Therefore, we can write this as 2RA is equal to mg, and therefore we get that our RA is equal to mg by 2, which is nothing but equal to our RE. Okay, either way, we are going to get the same answer. Now, we come to our second part, and second part we are going to find out the internal forces in each beam. And all these triangles are equilateral, so the angles will be of 60 degree. All the angles are of 60 degree. So let us start with this point C, and we say that we have our joint C, and for this point C, so this is a C point, and we have this is our BC and DC, and they will be both making an angle of 60 degree with the horizontal. So everything is in equilibrium, and we can also divide the forces of suppose BC. Okay, so we can divide this into our component. So this is our FBC, sine of 60, and this will be FBC cos of 60, and similarly we can write this as FDC sine of 60, and we get this as FDC cos of 60. So these are the forces acting on it, and furthermore we can write now for the vertical equilibrium. So for vertical equilibrium, okay, so this is our x-axis and this is our y-axis. So we can say our summation of forces for y should be equal to 0. Therefore, we can write that and here mg will be acting in downward direction. So we can say that our FBC sine 60 plus FCD sine 60 minus mg is equal to 0. And because of symmetric nature, we can write that by symmetry we can say that our FBC is equal to our FCD, and let us call this as our FS. So based on this, we can write this over twice Fs sine of 60 is equal to our mg, and from here we can find out our Fs. So Fs will be equal to our mg, and we have this as twice of sine of 60, and that will be resulting in square root of 3. So this is our Fs. Okay. And so therefore we can say this will be equal to our FBC and is equal to FCD. Okay. So this is our forces in our CD as well as our BC. Okay. And both these forces FBC as well as FCD will, you can say, they will be acting as a tension. Okay. So we can say, write this as a positive m square root of 3 and it will be a tension force, because we have to identify them as a compressive or tension. Okay. Now we come to our point joint B. And joint B, so this is B and A, and this B is also connected with our D, and along with it is also connected with our C. And once again, let me complete this triangle. So this angle will be 60, equilateral triangle, this angle will be also over 60, and this angle will be also over 60. So therefore the force that is a FBA or AB, it can be divided into furthermore two components. First one will be our FAB cos of 60, and other one will be a downward direction, that is a FAB sine of 60. Similarly, we are going to have this will be also over 60, and we can write this as our FBC cos of 60, and in downward direction FBC, and we have this as sine of 60. And between the FBD, the BD is in horizontal direction, so it will be having a force of FBD, and we have already defined this is x-axis and this is y-axis. Therefore we can write the horizontal equilibrium So we have our horizontal equilibrium, and this horizontal equilibrium we get our minus of FAB cos of 60 plus FBC cos of 60 plus FBD should be equal to 0. And now we come to vertical equilibrium. So we have a vertical equilibrium, and the vertical equilibrium, two forces, FAB sine of 60 and FBC sine of 60. So both will be in downward direction, that is negative FBC sine of 60. So this is, or we can take this as common, and FAB sine of 60 is equal to 0. And we can just a little bit solve it. So therefore from here we can say that our FBC will be equal to minus of FAB, and we already know that our FBC is equal to mg upon square root of 2. Therefore from here we can say that our FAB will be equal to minus of our mg square root of 3. And this is a negative sign. Positive we have taken as a tension, so negative will be our compression. So this will be our compressive. And we can furthermore substitute in this equation FBC is equal to minus of AB and solve it. Okay, let us call this equation number 1. So we can see from equation 1 we get minus of our minus FBC and cos of 60 plus FBC cos of 60 and one second, this should be like this, FBC and plus FBD is equal to 0. And this will be minus minus plus, and this is all be plus, so we get here 2BC cos of 60 to FBC cos of 60 plus FBD is equal to 0. Or we can write that our FBD is equal to minus twice FBC, and FBC is our mg square root of 3. So this comes as our plus mg square root of 3, and we have cos of 60. And cos of 60 is our 1 by 2, so 2 and 2 are going to cancel out. Therefore, from here we get that our FBD will be equal to minus of our mg square root of 3. And here also there is a negative sign, so which means it will be compressive. And now we come to our, I think we found out and rest we are left with our point A and C, and those we can call that solve it equally. Okay. So we can say that for, so let me draw it again. We have our A, B, C, D and E, and we have a angle of 60. Therefore, we can divide into two components. We get this as our FAB sine of 60, and we get this as FAB cos of 60. Okay. And so it means and for point B we already have the equation, which is our equation number 1. So let me write it once again. So you can say from equation 1 we have our minus of FAB cos of 60 plus FBC cos of 60 plus FBD is equal to 0. So this equation is already known to us. Okay. And also in the horizontal direction we are going to have for point A. So let me write it here. So we can say for joint A, horizontal direction, one force is the component of our AB and other one will be our FAC. Okay, so there will be two horizontal components. So we can say for joint A, horizontal equilibrium, and we can write it as FAB cos of 60 plus FAC is equal to 0. So it means FAC is equal to minus of FAB cos of 60, and FAB we already know, so we can simply substitute it. We get FAC is equal to minus of minus mg square root of 3, and cos of 60 is our 1 by 2. So this gives us that our FAC is equal to our mg, and we have 2 root 3. Okay. And it is having a sign of positive. Okay. So positive, we have already defined that it is having a tension. And similarly, we can also find out our FCE. Because of symmetry, we can simply put it like this. So we can say that because of symmetry, we can say that our FAC is equal to FCE, which is equal to plus mg 2 root 3. Once again, positive sign, so it will be a tension. Okay. So this was the first question. Okay. And now we come to a second question. The second question, it states that a ball of mass m is held against a vertical wall by a string as shown in the figure. The string is tangent to the ball and it makes an angle of theta with the wall. If the ball remains in static equilibrium and does not slip downwards, determine the minimum coefficient of static friction between the ball and the wall. So let us draw the figure first of all. So we are having a wall, and against this wall a ball is just touching it, and we have string which is acting as a tangent to this ball. Okay, so it is somewhere here, and it is making angle of theta with the vertical. Okay, so this is a basic figure that is as per the question. And so we can just say let r is the radius of this ball and m is the mass. Okay. And there is a tension T in the string. Okay. And we are going to have, along with this tension T, there will be two more forces. One force will be the normal at the point of contact, and other one will be the frictional force let us suppose that force is given as F, and we are given that everything should be in equilibrium. Okay. So we can just draw the forces and make in equilibrium. Okay. So we are interested in, suppose this is the vertical and this angle theta, we have a tension T, and this tension T we can divide into two components. So this angle will be also over theta, so we get this as T cos of theta and T sine of theta, and this is our this is a point of contact, let us call this P, and this is our O, and we are calling this as O prime. Okay. And we have a center C. Okay. Therefore, let me and we are going to have this, we have a center C. So in the downward direction we are going to have our mg, and at point P there will be normal, and this is our T sine of theta. So these are the forces that will be acting on it, and everything is in equilibrium. Therefore we can write that vertical equilibrium summation in y should be equal to 0, and we can define it as our, this is x and y. Therefore we can write that, okay, one thing I forgot to mention, there will be friction in upward direction. So we can say T cos of theta plus friction minus mg will be equal to 0. And this is vertical part, and now we come to our horizontal equilibrium. So which means summation of forces in x should be equal to 0, and we have normal, that is of n minus T sine of theta will be equal to 0, or we can say that our n is equal to T sine of theta. And we can also find out the moment equilibrium about the center C. Moment equilibrium about the center C. Okay. And there is a tangent force, that is our tension, and it is at a distance of r. Okay. Therefore we can say that our movement from tangent force, which is equal to our plus RT, and we can also write this as the moment from the friction friction, and that will be equal to our minus r times F. and their summation as per the equilibrium. You can say the summation of the moment should be equal to 0. Therefore, we can write that our RT minus RF should be equal to 0. And this gives us that our F is equal to our T. Now we can just solve the equations, and we are basically having two equations, equation number 1 as well as equation number 2. So from equation 1, we can write, we substitute value of F as T, so we get this as T cos of theta, and plus T minus mg is equal to 0. And now it is quite simple to solve out the tension T. So we can say tension T will be equal to our mg and 1 plus cos of theta, which will be also our frictional force because both are equal. And we can also find out our normal, because we know that our normal n is equal to t sine of theta. So we can write this our mg sine of theta 1 plus cos of theta. So this is our value of the normal. But we are interested in finding out the angle for the frictional. Therefore, we can say that for impending slipping, our F frictional force should be less than equal to our coefficient and normal. That is our limiting value. So we can say the limiting value or the minimum coefficient of static friction we can say limiting or minimum coefficient of static friction we can write that our coefficient and normal should be equal to our F. And from here we can write the coefficient should be equal to friction upon normal. And we already know both these values. Therefore, we can write that our the coefficient will be equal to normal is our t sine of theta and F is equal to t. So F is equal to t and normal is our t sine of theta. So this t and t cancels out. So we get our coefficient will be equal to 1 upon sine of theta. So this was our second question. Now we come to the third question. Third question, it states that a ladder of mass m and total length L rests against a frictionless vertical wall with 1/4 of its length extended past a supporting corner as shown in the figure. The corner provides the only frictional support needed to keep the ladder in static equilibrium. Assuming the ladder remains at rest, determine the total force exerted by the corner on the ladder. So we can draw the basic diagram. So we have a ladder and it is resting against the wall. Okay. So this is our wall and ladder is just touching the corner and it is to this wall, and it is making angle of theta with the horizontal. The total length of this is given as L, and its mass is given as M, and we are given that this extended portion beyond this corner is having a 1/4, that is L by 4. Okay, so this is our basic question that is given to us. And so let us assume that this is point A and other point we call as B, and suppose this is our O. Okay. Therefore total length is L by 4. Therefore we can say this length is our 3L by 4. And so we can so let me draw the figure, and figure we can, let me put it here. Okay, so for the sake of convenience I'm going to draw it again. So this is our point A, point B, and this is our point O, and we are given the length is our L by 4, and this length is our 3L by 4. Okay, so therefore we can write the position of A in terms of its coordinates. So we can say this is our XA, and this height of this point A is our YA. So we can say the contact point for contact point A, for contact point A, we can write that our XA will be equal to 3L by 4 cos of theta, and YA will be equal to 3L by 4 sin of theta. Okay, so this is our point A, and we can find out same things for our center of mass C. Okay, so the center of mass C is, let us suppose, somewhere here, and we have to remember this is with respect to our O. Okay. So for contact point A with respect to point O, and similarly we can write for our center of mass C. Okay. So you can say that this is our Y of C, and this is our X of C, and once again it is with respect to point O, and this length will be equal to our L by 4. Okay. Therefore we can say that for center of mass C with respect to point O, and we can write that our X of C is equal to L by 4 cos of theta, Y of C is equal to L by 4 sin of theta, and there will be a reaction, or we can say the normal, and this is our reaction force or normal, and once again we can divide this normal into two components. we can call this as our r of x, and this we can call as our r of y. And there will be a normal at point A, because A is also point of contact, so it will be in towards the left side, and let us call this as our H. And what else? I think more or less we require all these things. So we can say that we are going to define the forces, and we can say the wall exerts a horizontal force H, okay, at A, at point A, okay. And there will be a mg acting downward direction to the center of mass. And the second one is our mg acts downward at point C, downward at point C. And finally we can write that we have a corner reaction at point O, and that corner reaction is our R, which we can divide into two components, that is our R of x as well as our R of y. So we are going to calculate the moment about this point O. So we can say the moments about point O, and we have a horizontal force, so we can say for force H, let us call this as mH, which will be equal to the force multiplied by the lever arm, that is our y of A. And y of A we already know, so this comes as H 3L by 4 sine of theta. And next is our for mg, let us call this as moment of mg will be equal to our mg and the lever arm, that is our x of c. So this comes our mg multiplied by L by 4 cos of theta. And the last one is our, okay, because the reactive force we are taking at O, so the reactive force is not going to produce anything. And for equilibrium, we can write that moment of H should be equal to moment because of our mg, and we can simply substitute them. We get this as H 3L by 4 sine of theta is equal to our mg L by 4 cos of theta, and this L by 4 cancels out, and from here we can write our H is equal to mg by 3 cot of theta. Okay, so we got the normal force at point A. Okay. Now we can write the force equilibrium equation as well. We just calculated the moment equations, and now we can write the force equilibrium. And the force equilibrium, first is our horizontal, so which gives our r of x plus h should be equal to 0, or we can say our r of x is equal to minus of h we just calculated. Therefore we can write that our r of x is equal to minus mg square root of 3 cos of theta. So this is the x component of the reaction, and then we come to the vertical part. And vertical, we have our r of y minus mg should be equal to 0, or we can say that our r of y is equal to our mg. Okay. And from here we can easily calculate our this magnitude. We can say that our magnitude will be equal to r of x square plus r of y square and its square root. And mg we can take as common, and inside the bracket we are left with 1 plus, and 1 second, this is not square root, this is only 3. So this we get as cot square theta upon 9. So therefore, in case of especially in static equilibrium, we have to remember that the forces resolution is very important. If you are able to resolve the forces, you will be able to solve the questions quite easily. So the resolution of forces plays very important part in case of our static equilibrium, or in general most of the question in the physics except few chapters, you can just deal them directly by using the resolution of forces. Okay, because the resolution of forces are very important in that. And now we come to our final question, and it states that you hold one end of the stick of mass m, length L. A point located 1/4 of the way up the stick rests on the frictionless corner of a table as shown in the figure. The stick makes an angle of theta with the horizontal. Determine the magnitude of the force your hand must apply to keep the stick in the static equilibrium. For what angle of theta does the vertical component of your hand's force becomes equal to 0? So this case is a case of static equilibrium, and the resolution of the forces is going to play very important part in this. And we can just draw the basic figure. So this is our the corner that is given to us, and in this we are having a stick which is making an angle of theta, and it is held by hand at this point. So let us call this as our H, and let us call this as our S, and the total length is given as our L. And it is also mentioned that this extended portion is having a length of L by 4. Okay. And okay, So let me, okay, I'll just write it here. So there will be a center of mass. Let us put this is our center of mass, that is our S of C, and its distance from the hand will be equal to our L by 2. This is doesn't look good actually. Let me draw it again. Okay, so I'm going to draw this figure again. This looks a little bit asymmetric, and this is our point S, this is our H, and we have our L by 4. Total length is given to us as our L, and its mass is given to us as M. So the center of mass is somewhere here. Let us call this as S of C, and its distance from the hand is our L by 2. So these are the basic things which are given to us. Obviously at point S there will be a force, that is a contact, and let us call this as R of C. And okay, so let us consider a unit vector which is along this, the length of the stick, and this unit vector is, let us suppose, our U, and there is a unit vector which is also in terms of this normal, that is our N, and we can easily write the equation for, and the angle is theta. So we can easily write the equation for our unit vector as well as our normal. So we can say unit vector along the stick which we taken as U, and this U can be written as our cos of theta and our sine of theta, that is x coordinate as well as our y coordinate. And we have our a unit normal vector which we consider as N, and this N will be equal to our, because it is normal, so this will be minus sine of theta, and we have this as our cos of theta. Okay. And we have considered a reaction R of C, and its magnitude let us consider to be R. So we can say that the reaction magnitude is our R. Therefore we can write that our R of C will be equal to our R, and the unit vector is our sine of theta and our cos of theta. Okay. And we have considered that this is our x-axis and this is our y-axis. Okay. And also there will be a force because of this hand, and let us divide this into two components. Okay, we can just deal it later on also. Okay, let me write it, and direction we can just come out to later on, it's not a big problem. So we can say that the force from the hand, let us call this as force as F, and two components we call this as our F of X as well as our F of Y. Okay, direction we can determine later on as compared to their solution. So let us find out the moment at H. Okay, so remember this H is our hand. So we are going to find out our moment equilibrium about hand, and is basically represented as our H. Therefore, we can find out because of the weight. So we can say that our moment due to our mg, and let us call this as mmg, which will be equal to our mg times, we already know the, okay, we have to find out its coordinate also, but that's not a big problem. You can, let me redraw the figure. So everything we are dealing with respect to this hand, and right now we are having our this weight which is somewhere here, that is our S of C is acting in the downward direction, and this length is our L by 2 because total length is given as L, and we are having angle of theta. So we can easily find out the perpendicular lever arm of our this. So we will be having, this will be L2 cos of theta, and this will be L2 sine of theta. Okay, so we get this as our mg times L by 2 cos of theta. And next we are going to find out the moment of the corner reaction about the hand. Okay. So for corner reaction, this is our point S, and this point S is somewhere here. So this is our R, two components, R of X as well as our R of Y, and this is distance is given to us as L by 4. Therefore, we can say that our moment of corner reaction, and this corner reaction is having two components. So let us have moment our R. So first component will be our, we can write this our R of Y multiplied by, this is our L, this distance will be our L by 4 cos of theta, and this distance will be our L by 4 sine of theta. Okay. Therefore, we can write that our M of R will be equal to, we have our R of Y times L by 4 cos of theta, and plus R of X L by 4 sine of theta, and we already know that our, this is our X component as well as this is our Y component. Therefore, we can write that our M of Y will be equal to this comes as our r, and we can write this as our L by 4 cos squared theta plus sin squared theta, and we can take this as common. Therefore we get our m of y is equal to our r L by 4. Now we come to the static equilibrium, or we can say equilibrium because of the momenta. Therefore we can say that our equilibrium of moments, we can write this as our r L by 4 is equal to our mg L by 2 cos of theta. So this gives us that our L cancel out, 4 goes by 2. So we get that our R is equal to twice mg cos of theta. And now we come to our force equilibrium. So we have three forces basically. So force equilibrium, force F, and then we have reaction, and then we have a weight should be equal to 0 respectively in x and y direction. Okay. So let us write for our this x part. So we can say for horizontal, and horizontal we have our f of x plus r multiplied by minus sine of theta is equal to 0. So from here we can say that our f of x is equal to our r sine of theta. Okay. And then is our vertical, and vertical we have our f of y plus r cos of theta minus mg is equal to 0. Therefore we get that our vertical component f of y will be equal to our mg minus r cos of theta. And we know that our r is equal to 2 mg cos of theta. Therefore substitute it, we get that our f of y is equal to our mg minus twice mg cos of theta. And one second. Okay, and if we substitute in this f of x, we can write that above f of x will be equal to r is our 2 mg, so this comes as 2 mg cos of theta sine of theta, 2 mg cos of theta and sine of theta, which can be written as our mg sine 2 theta. So this is our x component, and for our y component this will be our, I think f of y, and we have a r, where we are, mg cos, so this comes as square. Okay, so let me write this one here. So we get our f of y is equal to, we have our mg minus r, and that comes to our twice mg cos square theta. Mg we can take as common, so this comes as 1 minus 2 cos square theta. And this can be simple trigonometric. So f of y is equal to our minus of, we can write this as cos 2 of theta, cos 2 theta. So we got both the components of our f. So we know that f was having two components, x as well as y. Now we can easily find out their magnitude. So we can say that our magnitude f will be equal to our fx square plus fy square and its square root. And we are having mg and mg, so we can take as common, so this will be coming as sine square 2 theta cos square 2 theta, that is 1. Therefore we can write that our f is equal to our mg square root of sine square 2 theta plus cos square 2 theta. Therefore is equal to our mg. So this is the magnitude of the force which was asked. Okay, and basically this f is independent of our theta. So it means that our force F, which was, let me draw this here, so this was our hand H, and force F was having two components, f of x as well as our f of y, and the resultant is our f, which we just calculated, and this f is independent of our theta. And we have second part. In this second part we have to find out for what value of theta the vertical component becomes equal to 0. So we have part B, and part B we are interested in vertical component. So force we already know that f of y is our mg cos 2 theta, and we need that our vertical component should be equal to 0. So we substitute f of y is equal to 0. Therefore this comes equal to 0. Or from here we can write that our cos of 2 theta is equal to 0. It's a simple trigonometric now. This comes as pi by 2, or we can say our theta is equal to pi by 4. So it means when the value of theta means it is the stick is making angle of theta with the horizontal. So when this theta comes equal to pi by 4, the horizontal vertical component vanishes. Okay, it becomes equal to 0. So this was the basic question. Okay, so today we solved 4 questions, and these 4 questions were from statics, or we can say force equilibrium also we can call it. So we have to keep in mind that in the resolution of forces plays very important part. If we are able to resolve the forces, we will be able to solve the question quite easily. Or in general, most of the physics questions are based on the resolution of the forces. Okay, not all, but most of them. Okay, so this completes all the 4 questions. Thank you.